Given, an integer array nums of length n, rule, a trionic subarray nums, L through R, needs 4 indices with L less than P less than Q less than R, nums, L through P, is strictly increasing, nums, P through Q, is strictly decreasing, and nums, Q through R, is strictly increasing. Return the maximum sum of any such subarray. Constraints, n between 4 and 10 to the 5th, values between negative and positive 10 to the 9th, a valid subarray always exists. Example 1. Indices L equals 1, P equals 2, Q equals 3, R equals 5. Indices 1 and 2 go up, 2 and 3 go down, 3 through 5 go up again. The subarray sum is -2 plus -1 plus -3 plus 0 plus 2, which is -4. That matches the output line. Example 2, the whole array fits. L is 0, P is 1, Q is 2, R is 3. 1 then 4 goes up, 4 then 2 goes down, 2 then 7 goes up. The sum is 1 plus 4 plus 2 plus 7, which is 14. Think of a trionic piece as one contiguous window with 4 hinge indices, L, then P, then Q, then R, all strictly increasing in that order. Between those hinges the array has to climb strictly, then fall strictly, then climb strictly again. Picture the toy walk 1, 4, 2, 7, the polyline rises, dips, then rises. The braces mark the 3 strict legs, the letters mark the 4 hinges where the story can bend. Those horizontal spans widen on purpose. The first line is only the current index, a possible new left end. The next span covers the first strict climb from L through P. The wider span adds the middle drop through Q. The widest span is the full trionic prefix through the last rise. The maximum answer will come from that phase. Sweeping I from left to right and keeping the best ending sum for each kind of partial shape is exactly dynamic programming. Next we attach the code names to each idea. Here are the 3 phase totals we keep while scanning. dpRise 1 tracks the best sum on the first strict rise, L through P, dpDrop carries the best sum through the middle descent, L through P through Q, dpRise 2 is the only state where all 3 legs exist, it holds the best full trionic shaped prefix on the final rise. The answer is the maximum dpRise 2 seen while you scan the array. Solution. 5 rows, column index, nums, then dpRise 1, dpDrop, and dpRise 2 for the 3 phases. Every dp cell starts at -infinity, not 0, entries can be negative, so 0 would be a bad sentinel. Under typical bounds near -10 to the 9th, that keeps empty state strictly worse than any real partial sum. Above the indices, green and red arrows mark strict rises and strict drops between neighbors. Let's trace the logic on a table. Each row is a phase of the journey. We fill column by column starting at the second index, because a transition needs 2 adjacent values. At index 1, values rise from 1 to 4. That begins the first rising leg, take the previous value, add the current, and store 5 in the dpRise 1 row. At index 2, we drop from 4 to 2. The first rise total of 5 hands off to the drop row, 5 plus 2 is 7. At index 3 we rise again from 2 to 7. The first rise can restart from 2 alone, so max of 2 and -infinity plus 7 is 9. The drop total of 7 feeds the final rise, 7 plus 7 is 14, a complete trionic shape. We track the best value seen in the dpRise 2 row. Here the maximum is 14. Notice how we filled the sheet. To get the answer at index 3, only index 2's totals mattered. Earlier columns were not reused. So we never needed whole arrays. 3 scalars updated each loop iteration are enough. Each step commits the next values into dpRise 1, dpDrop, and dpRise 2. That is the baton pass, linear time, constant extra memory. If the baton felt like a leap, spend a little time filling the 3DP rows on a few custom arrays until the pattern is automatic. That table practice makes the rolling scalar version much easier to trust. Let n be the length of nums. Time is linear, a single forward pass, and at each index we do constant work, compare with the previous value and update 3 rolling sums for the Trionic phases plus the running answer. Extra space is constant, a sentinel, those phase totals, the next step copies, and the running maximum, no tables or buffers sized with n. Define the routine that returns the maximum Trionic subarray sum. Initialize first rise with the first element as a one-element increasing run. Mark middle drop state as unreachable at the beginning. Mark final rise state as unreachable at the beginning. Initialize the best answer to negative infinity. Now scan from the second element to the end. Reset the next first rise state before applying transitions. Reset the next drop state before applying transitions. Reset the next final rise state before applying transitions. If the current step is strictly increasing, update rise transitions. First rise extends the prior first rise or restarts from the previous element alone, then adds the current value. Final rise takes the better of continuing after a drop or extending an existing final rise. Else if the current step is strictly decreasing, only the drop transition is valid. Drop takes the better of starting from the first rise or extending an existing drop. Commit the new first rise value. Commit the new drop value. Commit the new final rise value. Update the answer with any valid final rise total at this index. Return the best Trionic sum found.